यार एक माउस, तुम्हारे पास माउस है क्या? एक माउस मिल जाएगा? हेलो। हेलो। Okay, so in this case, we are discussing the model for fault displacement patterns. So in the first case, we can have a propagation fold. You know, basically, you know, and in this case, it is there is a barrier, so it is kind of displacement is kind of restricted along the barrier. And in this case, it is propagating both sides, restricted at one tip, propagation towards the barrier. Both sides it is restricted, and in this case, it is restricted with both tips convergence on the semi-elliptical form and propagation of the barrier 30% of the all types. So fault displacement, linkage and evolution. So in this case, we can see that there is fault growth by radial propagation. So maximum displacement in one event, second, and then you have the third. So displacement along the fault can also vary. And in this case, we have these different A, B, C, D segments as isolated segments. And sometimes they can overlap and they can combine to become one fault. Like in case of Janori anticline in Punjab, we see this kind of a behavior. So the fault basically started to grow in, there are two different faults and they basically merged along the Sondun and they formed this Janori anticline. So we can have the linkages of the faults. Different type of faults. So in this case, again, displacement compensation along the multiple faults. So we have these multiple faults, they're interacting and we can have the throw, combined throw time. Again, these two faults are merging and then we can have the damage zone in between those two faults. And some of the geomorphic expressions of the strike slip faults, like in this case it is dextral and sinistrals, and I think everybody knows how we can calculate whether it is a dextral or sinistral fault, right? And along a strike slip, so these are the geomorphic expression of a strike slip fault. Like in this case we have a linear trough uh, commonly form along the principal displacement zone because structure blocks are slipped past each other along this zone, and because of the fracture material are more readily eroded along the fault zone. So in this case, if we have a strike slip fault, we can have sag ponds, we can have pressure ridges, we can have scarps, we can have deflected streams, we can have benches, and these are shutter ridge. So these are different features which we see when we see a strike slip fault. Because in Himalayas we have a lot of vegetation, and there is sometimes what happens is that the strike of that also creates an impression that there is some kind of a linear feature is going on, but most of the time these are just the bedding plane of the rock. So in Himalayas it is difficult sometimes to figure out or find the active fault or a expression of an active fault. So in that case we have to rely on different geomorphic markers. For example, sag ponds, if you have a chain of lot of these ponds which are in a linear pattern which are formed, and then we also take the help of remote sensing. Basically, in the afternoon, we will show you some cartosat images in which you can see in 3D. You can see the ground in 3D, and you can have a sense that one block is uplifted and other is down. And then you can trace out that fault along its length. Right? And then once you are convinced that yes, there are many geomorphic markers which are present along the trace of this fault, then you can decide that okay, if you want to go for field work, then you should know before that, which kind of features you want to see or observe in the field. It's not like you just go and then try to search because you want to optimize your time in the field. So this is a we have very good. We have two examples very close to Chandigarh. One is the Sabilpur strike slip fault, and Taksal Sabilpur Taksal strike slip fault, and other is in the Saton region where you can see different stands of MBT which are behaving in a strike slip manner. So geomorphic expression of a strike slip fault, we can have sag ponds, and this is the fault and the scarp. So scarp basically means that you have some kind of a step-like feature, and when we are talking about scarps, we don't want to consider river scarps because river scarps are formed because of erosion only. We want to understand that this is a tectonic scarp. So tectonic scarp is a step-like feature which is formed because of a displacement along a fault. So we are also looking for some scarps, and in remote sensing images, sometimes we can see the changes in elevation. Sometimes elevation changes are good, but sometimes they can be of the order of 1 meter or 2 meter, or less than that, or maybe 10 centimeter. So that we have to figure it out using remote sensing. We use remote sensing for that. We go in the field also. We use GPR, ground penetrating radar, in order to locate where is the fault in the ground, because most of the time maybe we are able to find the expression of the fault on the ground, but when we go in the field, in order to pinpoint the fault we need a lot of techniques in order to see where is the fault. So geomorphic expression of a strike slip fault, when a ridge that has been translated along the fault subsequently blocks a drainage, it is termed a shutter ridge, and we have examples of this on the both the upstream and downstream side of a fault. River terraces may be systematically offset. If a strike slip fault is going through, let's say, a river terrace, you can see that these river terraces are shifted. A geomorphic expression of a strike slip fault, commonly streams crossing a strike slip fault will exit from a mountainous terrain into a gentler one. Scarps are also an indicator of a strike slip fault. On the downslope side of the strike slip faults, beheaded stream valleys may be preserved. A geological scarp, we can see that in this case, we have, some striations we can see on the fault scarp. Dip slip fault are inclined fractures where blocks have mostly shifted vertically. So geomorphic expression of normal or thrust fault, unpaired normal faults creating half grabens or half fault angle depressions occur more commonly. The down-dropped hanging wall of a normal fault commonly generates a basin in which the sediments accumulate. Many normal faults bounded asymmetric ranges with one step fault bounded flank and a gentle sloping large to unfaulted opposite flank. Normal faults can omit the stratigraphy of the region and can push the older rocks on top and the younger to the bottom. Formation of a valley is also an indication of a normal faulting. Geomorphic expression of normal and thrust fault. Secondary synthetic dipping in the same direction with the similar sense of throw, or antithetic dipping in the opposite direction with an opposite sense of throw. Faults may be developed within a hanging wall block. Uh, in basically we are in the very close to the front. So here the Shivalik rocks, we can see that Shivalik rocks are thrusted on top of younger Indo-Gangetic plain. So in this, we have these different type of fault geometries. So now we are talking both of a fault and a fold, you know. So fault and a fold now both are occurring in the same place, and it is as sir has discussed these, shear zones. They are basically high temperature, but in our area here you can have a fault and a fold. So in this case, in the first example, this is a fault band fold. So the solid line represents the fault plane, and the rocks on top of the fault are making a fold. In most of the cases, they are making asymmetric kind of a fold. So second one is fault propagation fold, and third is the fault detachment fold. You can have the compression. So in this case, the fault is not coming up to the surface. In this case, the fault is somewhere down. So the fold is actually an expression maybe of a fault. You know. So beneath Chandigarh also there is a fault which we call as Piedmont fault. Maybe we can have some expression of that Piedmont fault in the you know southern side of the HFT. At some places we see the Piedmont fault, but in this region we have not seen any expression of that so far. So these are different type of fault and fold models. Basically, fault band fold model in which you can have the basically the layers are horizontal in this case, and then they are bent along that fault plane. Fault propagating folds, uh, different type of detachment folds. So basically in this area what we have learned is that you can have a fold, and below the fold. So now I will take some, for example, uh, the geomorphology of the Chandigarh region. So as I just discussed, that why don't we have floods in Chandigarh? So all of us know where the Sukna Lake is, right? And we have visited the Sukna Lake. So if you go to Sukna Lake, there are two types of mountains. First is the small one, and then you have the higher elevations. So these small ones are representing basically the Shivalik hills. And below that, you have lesser Himalayan rocks. Those are high in elevation. So Kasauli, we can see Kasauli, in a clear day from Sukna Lake. So the question is, one question is that what is when these formed? Why did they form? So we can think of the how this geomorphology, how this Chandigarh has come to its present configuration, geomorphic configuration. So this is a geological setup. Right here is Chandigarh, and skip it, चले गए नीचे. Okay. So right here is Chandigarh, and we have one river, Ghaggar River and Satluj River, and this is the Chandigarh anticline basically. And there is another anticline, Jhanori anticline, I was telling. So now you can think of that this Chandigarh anticline when these rocks came up, right? And there is a one more important thing is that there is HFT here, Himalayan frontal thrust is there. So as I just was telling that these are the younger rocks and these are the older rocks, as we can see in this image. So this is a cross section along this in a geological map. In that, what we are able to see is that Himalayan frontal thrust, it is northeast, and then you have a back thrust basically which is dipping towards south, and in between these two thrusts this Shivalik rocks are folded in this sense, making an anticline. And then you have other thrust, Sohn thrust, you have then Jwalamukhi thrust, then Paror, and then you have MBT. And if you drill in Chandigarh, if we see that only alluvial. And if you drill, we will find upper Shivalik rocks, and then you will have middle Shivalik, and then lower Shivalik rocks. And this is again, you can see that. So now, if we see, like, Dehradun is here, Nahan is here, Chandigarh is here, and then anticline. So HFT is basically a fault which is going into the ground, and then these are shivalik rocks which are folded. Actually, it's making a kind of a anticline in this area. Okay. So there was a paper by Vimal Singh and Tandon. Basically, they explained that in this area, what so Chandigarh is right here now. Chandigarh is, this is the Sukna Lake, and these are the small mountains, the outermost Shivalik hills. So if we can think of that, if these mountains are not there, right, at one time, so the water from the sub Himalaya will directly come into Chandigarh. It will cause flooding. Will cause, if we go some years back, when uh, these rocks were not folded, you know, so there were some rivers which were directly coming through this anticline into the Chandigarh area. So these are just morphometric indices which are used to understand. I will just discuss the results. So this is again an important observation. There is one river, Ghaggar River, in which we have a lot of river terraces, and this is the Satluj River. So one important thing which we can think of is that there is you can see that this is around 300, and Ghaggar River is at a approximately higher elevation, let's say 400. And this Chandigarh anticline, this segment is have lot of these wind gaps also, you know. But in general, Chandigarh is somewhere here, right? So if we take a mean elevation somewhere, then we are at a higher elevation as compared to the Roped area. So what happened in this area? Basically because of compression, we have compressed the Shivalik rocks, and these Shivalik rocks are making this anticline. And Sukna Lake is somewhere here, right? So these rocks are folded along a fault, basically. So this is this then this is the model basically which shows previously the all the water was coming directly into Chandigarh. Then there was an introduction of this thrust, injore thrust, and then the introduction of HFT and Sirsa. And because of this, then you have folding of these rocks. So when these rocks are folded, then you have this outermost Shivalik. That is the formation of your Chandigarh anticline. So this is the model, right? Before that, the rivers used to come directly from the Kirtarpur fan into the Chandigarh region. And when these rocks are uplifted, now the rivers are deflected in the Pinjore zone, so they cannot directly come into Chandigarh, right? So this is a kind of a geomorphic evolution of Chandigarh. We can say that we have very good drainage pattern. The city is built good, but the planners who planned the location of Chandigarh, they were very smart people. They knew that Chandigarh is lying at a higher elevation as compared to others. So the water which comes from this drainage, it gets into the Ghaggar River, or either it is diverted towards the Satluj River, but it does not come to the directly to the Chandigarh. And there are tracks of the older river which used to flow. If you go in this top of this anticline, you will find sediments, you will find terraces which are present in this area. So if we date those, then also we can calculate what was the uplift of this anticline. What was the uplift of this anticline, because we know the height, so how it came up. So that can be dated. Okay. Any questions in this? So this was just the model given by the authors. So these rivers are coming, and there is another thing. Now this anticline does not just come in one day. It propagates. It basically grows in both the directions, east and west. So slowly this anticline started to grow, and then river started to deflect, and then this anticline is growing on the both sides, towards Ghaggar and towards Ropar. So this is the final, you know, uh, This is the present day configuration, you can say, of Chandigarh in terms of geomorphology, right? So these Shivalik hills are actually helping us, or saving us from floods. But on the other hand, you have a fault also beneath these. So that can cause a big earthquake, you know. So whether they are helping or not, that you have to think. So this is the reference, the paper from which this material is taken. So these are the slides I just took from Professor Alexander Storm. And sometimes we can have earthquakes, and earthquake can cause a rock slide, and that can again cause a long run out. You know. So in 2008, Venchua earthquake in Bichua in China, that caused a earthquake caused rock slide that caused a dammed lake. A dammed lake is formed, and because of that, you have outburst, flood, and then you have aggradation. So this town was destroyed because of a earthquake. So an earthquake can have these multiple chain of events where you can have, a landslide, a rock slide, a big rock slide, and maybe a dam is formed. And now this dam is breached, and now this water will go downstream and it will destroy various things. We know that in Himalaya, in India, Himalaya has the maximum seismicity, and we have a lot of dams here in Himalayas, right? And the second state where we have maximum seismicity is in Gujarat. So we need to understand that, how these faults are going to behave in future. So I just want to show these two slides. This is one of the best examples of large earthquake that produced surface faulting and triggered numerous landslides, including giant rock slides and rock avalanches. And this was in 2008 in Venchua earthquake. So you can see in this diagram that this is the fault, rivers ruptures, and these are the landslides. You know, earthquake-induced landslides. So you can have a lot of these earthquake-induced landslides also. So in this case, they are showing, this is the fault trace, and there is a 10-meter of rise, 10-meter of rise of the land after the earthquake. So you can see this, this whole building is going up because of this earthquake activity. Okay, a little bit, I think I want to show some things here also. Yeah. So, yeah. So you can see that this is a figure from Jackson's. So you can see the epicenter earthquakes, right? So you have lot of earthquakes in the Himalayan belt, but in India, more or less earthquakes, and in Gujarat, some seismicity. But in general, you can think of that, the active deformation. Basically, active deformation means where you have today earthquakes. So those are the places where the earth is deforming in present times, right? So earthquakes shows us that where the earth is deforming in the present time. So in this figure, we can see that, you know, and there is another thing, because India is formed of various cratons, So cratons are again places where you have lower temperatures, lower heat flow, and in the oceans, basically, it's not that once your temperature is above 450 degrees C, then you don't have much earthquakes, because in oceanic crust is basically a homogeneous crust. But in case of continents, or in the continental landmass, the rocks are much more heterogeneous, and the concentration of uranium, thorium, and potassium, the heat-producing elements, that is not uniformly distributed. So because of that, you can have different type of geotherms, and those geothermal gradients again basically can control the depths at which you can find these temperatures. So the temperatures can vary in the depth. So ultimately that will again control the depth of the earthquakes in the Himalaya. So basically, temperature again has a very big control on the depth of the earthquakes. Okay, so we have a active fault in. So I want to just show this. This area is very close to Chandigarh. This place is known as Khetparali, and there is a strike slip fault. This is Sabilpur fault, and the expression of this fault is it is displacing actually HFT here also. And this fault is basically, if you okay, you tell me what is the movement along this. Is it a right lateral or left lateral fault? If you see this, Shefali. Okay, so if boundary is displaced like this, right? So whether it is, yes, left lateral. Okay, good. So yes, we can see that this is an left lateral fault. So the Ghaggar River is somewhere here. And, so we see this very clear cut, evidence that this is a strike slip fault, and there are some streams which are deflected, and there is Nahan thrust, and MBT is also very close. So this area is very important, basically in terms of understanding. And there is also a landslide here in this area. There is a big landslide, and all that material of that landslide is deposited right here. We have not dated it, but if we date that material, we can correlate it with the event in the past. Because the landslide just happened here, and the material is just deposited at the toe of the landslide, which has not gone further away. So that kind of material can be dated, and it can be known that what kind of a event, maybe paleo event, has triggered that landslide. Okay. So there are some things to understand that yes, we have HFT which is dipping towards that side. We have a strike slip fault, and this strike slip fault actually we published a paper. There was a problem because on a now you see this is approximately 2 kilometers, approximately 2 or 1.5 kilometer of displacement along this strike slip fault. And geologically, and if we go in the field, we can see that the rocks are displaced actually. We can see the rocks are dipping towards north, and they are displaced. That is totally fine. Geologically, this fault is a left lateral. But we published one paper and we said this is a right lateral. Currently, it is right lateral. Because geomorphologically, the displacement of the streams and the features which we see in this area shows that there is some kind of a right lateral movement. But geologically, on a longer time scale, it is left lateral. So basically, in this case, what we have is we have upper Shivalik rocks; those are over thrusting, and the other important thing is that here there is a river. This river has got 20 meters deep, and the fault section is exposed. So that is again an advantage for a geologist to go in the field and see this site. So the HFT, which is Himalayan frontal thrust, this is why I will say one of the best sites to go, and you can see that this fault is exposed. So right here what you see is that the fault is somewhere here, right? And the rocks behind that are making a anticline. you know I just showed you that then we can have a fault, and on top of that we can have a fold or an anticline canal structures. So and in this area we are able to see even 1 centimeter small folds, very very good folding basically in soft rocks. Generally, we think that a fold will form in a ductile or at a higher temperatures, but these are at very shallow in sediments. We can have folding also. So yes, so this is how it looks in the field. So this is a river terrace. On top of it, you have a river terrace. You also have a anticline. You can see this mudstone is going like this, and sandstone is also, and fault is somewhere here. You have fault, and this fault was discovered a long time back in 1985. This is one of the papers They have described these fault, basically this Khet Raleigh. And this strike slip fault, you can see that it has different geological formations in this area. So the red is basically tetrode formation. You see this orange color, that is basically tetrode formation. So tetrode formation basically seeing the Pinjore formation right here. So geologically, you can see that different layers are, you know, placed along this fault. And the other important thing is that we have Nahan thrust and then we have main boundary thrust, which is within a distance of, let's say, 6 kilometer. Within 6 kilometer, you have these three main, thrust faults in a small distance. Now, uh, some things we are able to understand in this area, some things we are not able to understand. For example, here you have upper Shivalik rocks, but in between this contact, we have middle Shivalik rocks. And so this contact, here you have upper Shivalik, here again you have upper Shivalik, but in between you have middle Shivalik sandstones are popping up in this area, and they are making the contact. And this is Tikkartal region. This is Tikkartal, and in Tikkartal also there are so many active faults are present, and there are expressions of landslides. Looks like due to induced, maybe due to induced earthquakes. So this is how HFT looks like in the field. You can clearly see here that you have, uh, material or endoganglic plain material here, and this is petrot formation. These are basically clays, petrot formation. So the clays are overriding the older rocks. So these are like 2 million-year-old rocks, and these are very young rocks. They are thrusting on top of rocks. So this is how the HFT looks like on the one side, on the right side of the river, and this is on the left side. So approximately 10 meter of, this section is there where clearly you can see. Now the problem in these rocks in the upper Shivalik is that these rocks are very soft rocks. These are mostly clays, sandstone, so like that, especially the upper portion. And on top of that, you also have a capping rock in this area. So there are two river terraces, T2, T1, and they are paired river terraces. Both sides of the fault they are preserved actually. So these are paired river terraces. Now, uh, only in this area we find river terraces more or less here and one more T3 surface is there. So they are very close to the fault, right? But after that, you don't. The river basically starts meandering. Only here, close to the fault, the river makes a V valley. Clearly these river terraces are formed due to folding and activity along this fault, because only here we are having these river terraces. Once we cross HFT, then we don't see river terraces. Okay, these are some deformational. This is how the fault plane looks like. So you can see this deformational pattern. The soft rocks, basically these are clays, and I also saw silicon sites in very soft place. Again a picture of and then this anticline is there small. This is the core of the anticline and we named it as Caproli anticline. Very small. You can see this folding here. These type of different deformational structures we find at kind of shear sense indicators along the fault boundary. And this is a anticline, basically anticline which has retreated back, you know because of erosion. Again, another site where a fault is present. So you can see boulder conglomerate formation on one side and cutout formation on the other side. So that is a clear-cut indication of a strike slip fault because along the strike, the rocks are changing. Okay. And in Google Earth also, you can clearly see, the topography. You can see that, this river was coming and suddenly start following the strike plane. And on the other side, it is totally different. And this fault is very clearly visible even on Google Earth. In the field, we were able to identify the fault. It looks something like this. Again, the fault, the strike slip fault. And what happened in this area? Once you go in the field, you will see some feature. Next year, rain will happen and it will erode the feature. So because it's a very fragile area, so next time maybe you will not find this same feature which you see. It is better to take the data at that time. All plane. And there are some tilted deposits on top of that. Again, we are seeing some expression of a fault. Okay. Then we also do trenching. We make trenches, for a fault, and then we do extensive field work. We use GPR in the field in order to find where is the fault, and then we dig a trench. Trench is basically you make a big, uh, ditch into the ground, and then you want to see then where is the fault actually. You clean the walls of the trench, and now you can see that in this case, this layer is here and this one is here, so it's displaced. This is along this strike slip fault which I just showed you, the left lateral fault. The you know so in the Saton area, very there is a big landslide. Now I would like to to show some of the work which we have done in this area. This Saton landslide is actually looks like something like this. This road is going like this, and this whole material, this road is coming down every year, like 10 meters down. And civil engineers go there, they think, okay, we can do something. And they're trying to stabilize also. But when we went into this area is tectonically very active, I will say. And there are a lot of thrusts which are coming close, or which they're crossing within this landslide. And this landslide is happening basically inside a lower Shivalik rock, lower Shivalik sandstone. So this is a geological map. So in Chandigarh is somewhere here, and this Sotan is here. And one important thing I want to point out that there is a fault which is known as Yamuna Tier fault. And a lot of people have marked it like this, and some people like this. And we were able to find that fault in the field, and we have made a trench on the fault, on Yamuna Tier fault. That fault also basically is an active fault, and it passes through this landslide body. So in this figure, you can see this is Ponta Sahib, Dehradun area. So Yamuna Tier fault is going somewhere here like this, and it is crossing this landslide, the Saton landslide from north south. And there are more faults which are coming east west. They are also going through this landslide. That is the reason. That is the only reason we have landslide only here. Along the whole strike of this road, we don't have landslide anywhere else. So why only at one place we have landslide? Because it has crushed and crumbled the rock from the both direction, from north south and from east west also. That is one point. And the second point is that uh, Yeah. The second point I want to make is this. So now this is the Saturn area. So there are one fault, MBT, MBF, DF, and there is a Sirmori Tal fault. Again, it is crossing. There is this Yamuna Tier fault. And if you see this whole area, if you see this whole zone is a kind of a paleo landslide site. Whole this sandstone is gone down because this is strike parallel, this is lower Shivalik. So within the paleo landslide site, only this small portion is active as a landslide. So when we are just looking on the road, we just think that this is the landslide. But actually the whole landslide is a bigger, is of a bigger size. And within that paleo landslide, only small portion is active. So we think that this bigger landslide happened might be due to a tectonic activity in the past. Okay. So you can see that this, there is this ridge kind of a curve, and we see these faults in this cross section clearly. We see this 10-meter cross section that these sediments are deformed and crushed. So wherever I went in Himalayas, most of the time I find that in faults we in landslides we see signature of some kind of a fault or a thrust zone most of the time. If you see inside the body of the landslide, if you search, okay. So yes, you can see, there is a lot of crushing and crumbling of the rocks. Okay. Now, I would like to show something. So I would like to show you some more examples where we are able to find the faults basically inside these. Uh, ये कैसे चल रहा है यार? Okay. So uh, one more thing is that we made basically we worked in this whole area from Chandigarh to Kotdwar, and we made geomorphic maps of this area, and we marked a lot of active faults in this area. So for doing that, we procured cartosat data from Indian Space Research Organization (ISRO), and then we are then using a software we can make a anaglyph. In anaglyph, basically we can see the 3D. We can have a 3D view of the area, and by doing that, we can see topographic changes, and then we can try to mark where the fault is going in the field actually. And using those, uh, then we are able to make these tectonic maps. So in Dehradun area, basically this fault is there, which is actually marked as a thrust. But at some places, we think that the northern side has gone down. And there are reports from Nepal also that MBT is showing that southern side has gone down. The northern side has gone down. So even though it is a thrust, it is showing that it is going the opposite way. So this is basically your main boundary thrust. Some of the places it shows that maybe your northern side is going down, and we see these kind of signatures some places against on landslide. Yes, there is this zone deformation zone. Road has gone down 3 times. Then there is another landslide which is known as Umri landslide. In that landslide also, this is very close to Chandigarh. We again see this is the Strikely fault. There is a Umri landslide, a big landslide, approximately 1 or 2 kilometers. And at the toe of this landslide, we again see signatures of some strike slip fault, and also in the body of the landslide. So this is how it looks. The landslide is a big. This is Ghaggar River, and at the toe, landslide find signatures of faulting. And here also we are able to see some normal faulting going on in the this landslide. This is how it looks in the field, and this is the joint data. So basically, when we are working with landslides, simply we can divide landslides into two categories, like either it's a rock or soil. If it is a rock, then it will have a lot of discontinuities, a lot of joints, lot of fractures. So when we go in the field, we take all the joint data. We try to take that all that joint data, and then we try to assess the slope stability of that area based on slope mass rating. In slope mass rating, basically we try to give a number from 0 to 100. If we are giving 100 marks, that means it's a strong, safe site. If we are giving less marks, that means it's poor quality or it can have destabilization, right? So it can be unsafe. So you can see that there is another then fault plane. We have drawn the fault plane which is crushing or crumbling this whole rock mass. So in engineering geology, when we say discontinuity, it includes any kind of a fracture, any kind of a joint, even fault, you know. So discontinuity includes everything basically. So this is again, in the field, this road was there, and then we were able to take the data of this, the fault which is present in the body of this landslide. Now this road is diverted because this road has gone down. It is diverted from the other side. Now this is a special case. In 2017 in Mandi in Himachal Pradesh, there was a big landslide. The name of the landslide is Katrupi landslide, and a lot of people have published a lot of papers in this area. You know what happened is there was a road, and suddenly during heavy rain, this whole rock mass collapsed, and the two buses gone down, and everybody died. So we also studied this landslide. So the important thing is that there are two salt mines. One is Dara, other one is Gumma in this area. And in between, strike parallel, this is the location of the Katopi landslide. So this is the Katopi landslide. And this is the geology which was given by previous workers. So they have reported that there is salt in one of the formation, Ropri formation. Ropri formation is somewhere. This is known as Lokhan, which actually contains rock salt also. So this rock salt is protologic in age, and we can see that this is the contact. So this contact is kind of a tectonic plate because these rocks are Precambrian and these are shivalics. You know. So when we went into the field, first time, uh, first of all, this is what we saw. That this is my student Abhishek, and we saw that there is a dome kind of a structure which is coming out of the landslide body. So you can see that within the landslide you have a volcano kind of a small crater, it's coming out, and these kind of structures are popping out of ground. So we think that there is a role of rock salt in triggering this landslide, because this landslide was a cyclic landslide. People have thought that every 20 years it starts to go down, you know. So we submitted the paper, and also along this landslide, I am able to find this limestone rock, which is a crushed rock, basically, which is MBT, you know. And I was able to see that this is the fault plane. I mean, it's going, and we were able to recognize that yes, on the right side of the landslide, we are able to see, because MBT is a older fault. So we are able to see that in the uh, now if you see this image, I have taken this image from a distance. So this is the dome basically in the center of this landslide, and this is the scale. Abhishek is going with GPR, and you can see this kind of a dome is coming up. Now this dome is covered by the sediment which are coming from the right side of the landslide, because now this dome is covered, but still it is rising. So what we have done is we have gone 3 years in this area, and we have done RTK survey in this area, and we are able to see that the rise is around 10 to 15 meters. 10 to 15 meters. the total rise from 5 to 6 years, you know. But this was, that is why it is very, very important when you are working in any area, you should always go in the field. You can do remote sensing, no problem. But that's just a tool. Just don't just rely on remote sensing. You need to go at the site. You have to check the site. You have to see everything. So this is the RTK survey. You can see that in RTK, you can see the uplifted zone within the landslide. Again, these are different surveys of the dome body which were done in 2018, 2022, 2024. So again, this landslide, the dome we have, this is the rise. It is not like everywhere it is rising. Some places it is rising more, somewhere less. And then rain is coming, and again some erosion is going on. So everything is going on in this. So we propose that causative factors, salt tectonics, fault, and rainfall. Previously, people said the maybe this landslide is triggered because of a just because of rainfall, or they might have just said that it is a seismic event or something. But we have added that basically what happened, lot of rainfall happened, water percolated down, and the salt became more and more beyond, and then it pushed through the fault plane of MBT, and then it toppled the rock above. And that is the reason, so salt tectonics, fault, rainfall, everything played the role basically in triggering this landslide. Another example from Uttarakhand. In 2018, we worked, one of my student did the PhD here. So basically, this is a Kalyasol landslide. So in this, we see this is a hard quartzite rock, very hard quartzite rock. And uh, you always have some landslide happening here, a lot of problems. So there are two things which we discovered in the field when we did field work here. First was that it's a plunging fold. It's a plunging fold, and it's basically plunging towards the road. It's like this. And always small chips are coming onto the road because of wind and other things. That is one thing we discovered. And the other thing which we understood from the literature, that there is a fault. The name of the fault is a Kalyasar fault, and it passes through this region. And you know we saw that wherever this fault is passing through, the rock is totally crushed and crumbled. But other places, you know that quartzite is a very hard rock. If you hit with a hammer, hammer will bounce back. But only at this place, by hand we are able to take out chips of quartzite of 1 centimeter only, by hand, because it's so crushed and crumbled. And again, the role of a fault. So along the road, this is a big landslide. There are more than 400 papers written on this landslide only. More than 200 papers. So here we see landslide. Here again we see landslide, and this place is very important. Number three, because here what happened is that, so Parvesh is standing. Uh, you know, so you see this quartzite is coming, dipping like this, and here it is totally crumbled. It started raining that time, and the water become milky. It is so crumbled and crushed. You can see that this is hard. Quartzite is coming, and here you have this crushed rock mass. And there is a contact, actually. There is, I think, basalt on this side. So we are not sure that whether, because I mean I think it is because of the, I will say that it is because of the fault, some past activity. So you can see what a fault can do. It can crush a rock like a powder. So that is the observation from this landslide. Yeah, in 2015, this is basically, now we are going to Manikaran in Himachal Pradesh. So in 2015, there is a place known as Manikaran where hot geothermal fluids are coming out of ground. So there is a Gurdwara and a temple there where people go for worship. And 2015, there was a big boulder. Big boulder came, and it came and destroyed the building. And this is basically the hot. This is a hot pool here. You can do swimming in this hot pool. So basically, we got a project from Department of Science and Technology, and we installed some sensors. First of all, the problem was to find out the place from where this boulder started actually. So elevations are very high here. You can see the rockfall started from some place here, and it bounced and it hit the Gurdwara down. And we did a lot of field work in this area, and you can see my student is standing. The size of these rock blocks is very big, and then we were able to find the site. A lot of debris is fallen there. There are a lot of unstable blocks. So the idea was to install a landslide early warning sensors at this place. So we did field work, we did drone survey in this area, made a lot of maps, and so we installed some sensors, crack meters and tilt meters. So we installed in this area, and we have 1 year of data of this. So the data is coming through into to our workstation in the department, and we have 1 year of data in which we can see these rock blocks are tilting or things like that. You know, so installation was what not very easy. You know, so we have to uh, have two ropes, one for safety and other is like rock climbing ropes. When we have the engineer and he has to drill actually inside, and also the mountain lion I think in the night comes in this area, and my student was camping here for 10 days, 10 to 15 days. So this is the data which we got from the sensors. This we will publish. Okay. Yeah. Any questions? Any this? Okay. I will very quickly I will show one paper which was published in 2023. So this is basically this is the area where we were working, and HFT is here. Mostly our work is concentrated along HFT MBT, but mostly the active fault is concentrated more along the front. So you can see Chandigarh here. Chandigarh is right here, and there is this strike slip fault. I was just telling the left lateral, right lateral. So this fault is going like this. Okay. And one more thing, if you see in Punjab, this Janori anticline, this anticline grow propagated from this direction, and this one propagated from this direction, and this area is uplifted in between, and you will find sediments of Satluj River when it was flowing from this area. So in Punjab also, the tectonics played a role in creating the Janori anticline. And if you see the Beas River was flowing from this area. But because of the propagation of this anticline, this area is uplifted. So because of that, this river is shifting like this. So it has to make a long turn because the land is slowly rising. So I will say the Planck model in which the topography slowly rises is more applicable, I will say, in this area because it's not just a sudden uplift of the topography. And then you have a lot of these drainages, your drainages are formed, and then you have these drainage density. In that, you can do morphotectonics. Basically, you can find some anomalies, some drainage is deflecting, things like that, in order to understand if whether there is a fault or some activity. That kind of exercises we will do in the afternoon, basically on. You can do it on computer, but we have made exercises so that everybody can do it on paper. So morphometric indices you can calculate. Okay. So, so basically, there is a very important. This Chandigarh is here. There is again this big fault, and it is going up to Dehradun. And this is basically the Katropi landslide. This area also we are working, and in the whole this area basically we are working. So for doing this study, this is the cartosat data. So you can see Chandigarh is here, the river. This is the fault I just showed you. And in the cartosat data, you can mark the trace of the fault. You can actually pick the trace of the fault, where the fault is on the ground. And then you can go. So these are like scarps. Scarps are like, some tectonic scarps. So the surface is shifted. And then you can try to date. You can go in the field, you can take measurements, and then you can try to date the sediments in order to understand when this deformation happened. Okay. So you can see this is Chandigarh, Sukhna Lake, HFT, and then this is Pinjore Garden. And there is again in 1600 there was a big earthquake which caused the step which is formed in the Pinjore Garden. You see this waterfall is there. So that is because of this earthquake activity in 1600s. That was just made a waterfall. Okay, and this is the geomorphic map of the same area. So you can see these different river terraces along Ghaggar River. 5 river terraces I was just telling you. So the Mansa Devi temple is also on a river terrace. So the river actually Ghaggar used to flow from this to it shifted actually migrated from right. And you have HFT. So along HFT you have uplift, and because of that you are forming these river terraces, and the river is also shifting onto the lateral migration of the Ghaggar River. So this side you don't have much. So these are basically representing unpaired river terraces. So in this area, basically in Thapli we put the trench. A trench was made. So this is again cartosat data. In cartosat data, you can see in 3D, and you can if you put glasses, we will show in the afternoon. Students will show some cartosat images in which you can see uh, perception, and then you can mark the different fault traces. And you can see this sag pond is forming shutter off ridge, and then the traces are coming of the fault. Now we know that the fault is going, but in this area, where to put the trench is a tricky job, even though you know the fault is there. But on the ground, to pinpoint where the fault is going, because sometimes we dig trenches, but we don't find anything. So that also happens. Sometimes, some failures also happen because, it is not like that you will always put a trench and you will find the fault. Some deformation, river shifting, and then some RTK data. This area was, mapped. Now this is how this fault looks in the river section. So we are looking towards north, and the fault is actually going north south. So you can see this is the damage zone. This side has gone up, this side has gone down, and there is a sandstone, lower Shivalik sandstone. Now this fault is actually an active fault. You know, very close to the active fault, you have sandstone and some deformation in the sandstone. But this side you have lower Shivalik rocks. These are basically clays, mudstone, very soft rocks. And the other important thing which we discussed is that we have quaternary deposits on the top, right? So we need these deposits because we want to date this, because these rocks, the age of these rocks is like 18 million or something. But we know from the definition of active fault, we need to have some sediments which are around 10,000 or 1 lakh, something like that, right? But 18 million rock, 18 million old rock, if it has displacement and it does not have any sediments on top, then you cannot tell that it's an active fault or something. So you need to have some quaternary deposits, right? So, so this is the river section. So, the fault is coming like this. So these are fields actually. So this field is this step is formed because of the fault. Actually, it is not human-made, terrace forming. No, it is actually fault is passing through this area. and we have done GPS profile, local station, and then we have to convince the farmers that we will put a trench here and we will, they have to be taken into confidence. So GPR, then we are able to make the trench dates, you know, and this is the interpretation like how this. So the three events were reported from this trench. So in this paper, it was so this fault is basically shown as a stream partitioning in this area, and this portion is logged. This portion is and this portion is basically creeping behind that. So it was shown that this area is strain is partitioned along this boundary. That is what is proposed in this paper. Okay. Okay, sir. I think I finished everything. Thank you. Okay. Yeah. If you have any questions, you can ask or discuss. Want to discuss something? Yes. Yeah. So one thing I think I want to say that when we collect this joint data in the field, so you can see this rock is dipping, and there are a lot of joints, and then those joints are used to do kinematic analysis in order to understand whether what type of rock failure can happen at that. So like we classify planar failure, wedge failure, toppling failure. And then some of this geotechnical data is you can put into a software and you can try to see the slope configuration, whether it can fail or not. So that kind of thing we can do when we go in the field. And no doubt we also look for some kind of geomorphic markers which can tell us that whether some kind of a fault is present or not. Because if you see this rock, it is not easy to understand that there is a fault is passing. So sometimes you have to see away from that side, not just at the landslide. You have to see a bigger view. You need to take a bigger view into picture, and you need to think that how this slope is different or anomalous from the other slopes, right? So in this case, we are showing the fault is there. This turning is there. So this thing you can do stereographic projections of kinematic analysis of different joint set data. You can show what type of joint failure will happen, and based on that you can again discuss that what kind of remedial measures you can provide to the slope. So this is what is a primarily step, and then you can collect more joint data, and then you can try to do some kind of a modeling, that you can do in rock science software. Okay. So I can show you some more work which we have done. Previously, HFT, previously, this is again one paper we have published. In this area, we were thinking HFT is a blind fault. Blind fault means it has not come up to the surface. But when we did field work, we were able to see that, fault is actually coming up to the surface, and it is also making the anticline in the Tripurali area. These are different river terraces. As I was just showing you that you need to also have some different river terraces, and then dating of these rocks. So now, Ishmeet, your answer to your question that you see my student is hanging there with a rock climbing rope and he's taking muscle samples. But this need to be done in a very safe manner. We had a lot of safety gear here. You cannot just do just by yourself. You need some teamwork. So this was the model which was given that, first the deposition and then some truncation in this area due to this fault. Yeah, this also I want to show. Now this area, basically this is Ganga River and this is east of Ganga River. This is Kordwar area. And in this area, uh, HFT is somewhere here. You can see HFT here, right? So now I was telling about a blind thrust or a Piedmont fault, a fault which can come ahead of HFT in the southern portion. So there is a river. This is known as Malin River, and this is Indo-Gangetic Plain. Now, this in this area you will not find much geological features. So we did some morphometric analysis in this area, and if you see this diagram very carefully, you will be able to see that there are some drainages which are formed in this area. New drainages are coming up. So we proposed that HFTs, but in this area, a fault is reported, you know, which is going beneath these sediments, and this area is being uplifted slowly. So if any area is being uplifted slowly, then in that area you will have new drainages are formed in that area. That is because water is the first. If you tilt the surface, the water will know. Okay, it will not go. It will go the down. So in this area, these new drainages are formed, and there is also deflection of this river which was coming. So it was coming like this, and now it is deflected. So using these two evidences and also some photographs, we were able to show that in this area, there is upliftment, and the fault is passing somewhere here. This fault is known as Najibabad fault in this area. So morphometry sometimes can be used to see or understand areas where we have no information. Okay. Okay, I think that's it for now. I went very quickly because I wanted to cover some things. Thank you. Sir, I think the data is with the uh, we don't have that kind of a coverage, but yes, small earthquakes, but the most of the data is controlled by National Geophysical Research Laboratory and some of the sensors, Wadia, and then uh, that is National Seismological Center. So they have, but we don't have actually. Yeah, but once I went to one place in Dehradun, uh, people, I have those figures. In one area, the river actually uplifted two times along the fault, and people visit every year there, thinking that some supernatural power is there. So the area actually lifted like this along the river. Some stresses are maybe released or something. But this is very important. Yes, your point. I also think that we should have some kind of a network which can observe where these earthquakes are happening. Any question? Oh, I think so. Then we can stop. Okay. Thank you.